can see it?
Yes, it's coming.
Okay.
Yes. Yeah.
Okay, so question 6 is asking us to find the inverse Laplace transform of a given function and to use partial fractions when it's appropriate. For this question, we're giving a function in terms of s. So we have f of s. And this tells us that we have a transformation of some function f of t, a Laplace transform of a function f of t. So what we want to do with this is work backwards to get our f of t. And in doing so, we'll have to use partial fractions. Like we're used to using partial fractions when it comes down to integration. It's like a nifty tool to put it into a form that's like when it comes down to integration, that makes it more that makes it oh my god, that makes your integral, your integrand integrable, or I don't even know if that's the word integrable, but it helps you integrate.
Inside the integral is called the integrand, yeah, right?
Yeah, your integrand. But in this circumstance, we're just using this algebraic tool to find our inverse Laplace. And it's just straightforward and simple. What we're going to do is factor out the denominator. In factoring out the denominator, what we're going to do is then multiply by multiply by the denominator. We want to get rid of that denominator, and in doing so, multiply by the denominator on the left and right side of the equation. And in doing so, we're going to have the numerator for the left side alone by itself, and on the right side, we're going to have these constants a, b, and c multiplied by these factors. And we're going to do a little trick in which we put these factors, we isolate these factors. What we're going to do is put s equal to certain terms and then get our answer for each coefficient, each variable. So for variable a, we set it equal to 0, and then we get that is -4/6. For b, for solving for b, we set s equal to -2, and then we get 22/5. Then for c, we set s is equal to -3, and we get 50/3. With that, we could substitute in our solution for these variables up top of our partial fractions right there. And then from there, we're now going to use our knowledge of inverse Laplace transforms. So like inversely doing a Laplace transform. So what you're doing is just like you're working backwards. So you have to know, like if you know the transform for a function f of t, then you can intuitively know the transform of a function inverse of the Laplace transform inverse of f of s. So that's exactly what I did right here. I know that in order to have a function that's going to be -4/s, right? You could just take out the constants to make it more familiar to you. I took out 1/6 for -4/6s. And in doing so, I knew that in order to have a result of a Laplace having some constant over s, you'll have to find a Laplace of a constant, So it's just -4 right here. And 4 over here is going to be e to the at that we're using, because notice how it takes the form of 1/s plus something. But traditionally it's minus something, so you know that it's intuitively going to be -2. So it's going to be e to -2t. And the same thing applies right here. It's going to be -3 because it's really 1/s minus some number. So you know that its original f of t would be e to the -et, and this is my answer, basically.
Okay. Yeah, very nice. I would factor out -4/6. Okay. All right. Anyone has any question? All right. Very nice. 均一。
So for this one, I'm presenting to like just find the initial value of the Laplace form using the Laplace form transform. Sorry, no something. Okay, so the given equation is y double prime plus 9y equals to 0, where y of 0 is 3, y prime of 0 is 6. So I use the sorry, I forgot to put the sign in, like the Laplace transform of y double prime is written to s squared capital Y of x minus s of y of 0 minus y prime of 0. And the Laplace of y is equal to the capital Y of x. So I plug in back to the equation, z equal to 0 and plus the 9y of x. So I factor out the y of capital Y of x times s squared plus 9 minus s times the y of 0 minus y prime of 0 equals to 0. And then I do the addition to the other side and division for the s squared plus 9. And then I plug in back to the numbers of y of 0 and y prime of 0, which is equal to 3s plus 6 over s squared plus 9. And then I separate them into two fractions. So 3s over s squared plus 9 plus 6 over s squared plus 9. And then I can factor out the coefficient, the 3 times s over s squared plus 3 to the square plus 2 times the 3 over s squared plus 3 squared, because based on the table of Laplace transform, so I do as let's see, y of s, so equal to the inverse of Laplace transform of 3 times s over s squared plus 3 squared plus the inverse of 2 times 3 over s squared plus 3 squared. So I can rewrite them as 3 times cosine 3t and plus 2 times sine 3t.
Great.
Okay,
Nice.
thank you.
Anyone has any questions? Right, very nice. Just miss the sign of L. Miss the letter L.
Yeah, from the beginning I have to write the equation.
Okay. All right. So I think Israel, your turn. Israel, are you here?
Yeah, sorry. I was just struggling for a second to remember.
Oh, no problem.
Hold on. Okay. That should be that. Share. Yeah, apologies. I was just a little slow with it.
Okay, that's all right.
So essentially, for 18.8, I just solved for the Laplace of t e to the 3t. So, plugging into the Laplace transform, what it will give me is the integral from 0 to infinity of e to the negative st times t e to the 3t, which just becomes, t e to the 3 minus st dt. I always forget the dt's. I usually ask that. Sorry. And essentially, because of the fact that we can, since we can take out, as was shown in our notes, we can take out a negative, which would just give us negative s of s minus 3t, which would make this very much more easier to calculate. Sorry. Let me get a hold of myself. Yeah, so once I get my my integral to t e to the negative s minus 3t, this will allow me to then do by parts, which I make my vt, which makes my d of e equal to 1. My du I let equal to e to the negative s minus 3t, which means my u, is equal to negative s minus 3 e to the negative s minus 3t.
Hold on 1 second.
Yeah.
So your v equals to t, but
Yeah.
your dv is not 1. What's your dv?
My dv would not be 1?
No. Your v is t. What's your dv?
My dv.
Something is missing.
Would it be dt?
Yeah.
Oh, yeah.
dt is different from 1, right?
No, but I do believe this is solving in terms of...
Doesn't matter what you're doing. You're doing partial, your differential, no, integral by parts.
Yeah.
dv, so v is t, dv is dt. Probably you mean 1 dt. dv is not 1, dv is dt.
dt.
Does it make sense?
Oh, yeah, because I completely... Oh, yeah, now I see where I messed up a little, because I completely forgot over here the dt again. Okay.
Yeah, probably you mean dv equals 1 dt.
Yeah, okay.
That's why you have 1 there.
Yeah. So then plugging it all in, it should be t e to the negative s minus 3t from 0 to infinity minus the integral from 0 to infinity minus...
Also, sorry, let me stop you one more time.
Mhm.
Also, you see your dv?
Yeah.
Your dv is in partial notation. Here is not partial. Here even is integral by parts, but it's not partial derivative. It's dv, it's lowercase d. It's dv, it's not this partial v. Or maybe that's your way of writing the lowercase d.
Yeah, that's my handwriting. Apologies about that.
Oh, okay.
These are all...
But this looks like a partial. You know what I'm talking about? When you take a partial derivatives, this is a notation for partial derivatives. Yeah. Okay, anyway.
Yeah. Okay, yeah, I understand. My bad. I'll try to make that clear more.
Okay.
Yeah, so so plugging into the integral by parts, this gets us the equation below, which is from the other part would be minus 0 to infinity negative s minus 3 e to negative s minus 3 t dt, but I forgot the dt. So of course, the left part of the integration by parts we can solve as a... I forgot the name of that thing. Yeah, we can solve it as a limit. So essentially, by doing L'Hopital's rule, we can find out that this as it goes to infinity is equal to 0. And because also t is a part of the function.
Hold on 1 second. Okay. Well, because I cannot. Let me make this a little bit bigger so I can see clearly.
Do you want to zoom in a little?
No, I zoomed already.
Okay.
So you were saying you can apply L'Hopital's rule. Tell me why. But L'Hopital's rule, needs a prerequisite condition. But I don't think that yours satisfies that condition. Under
Really?
what kind of situation, right? So when do you apply L'Hopital's rule?
I actually don't. I don't know. I'm just so...
L'Hopital's rule you can apply only when you have the indeterminate form, 0 divided by 0. You have to rewrite this. If you rewrite this, yes, you can apply L'Hopital's rule.
Okay. I thought I could. Apologies, but...
You see how you can rewrite this function? So your function is t over e to the s minus 3 times t, right?
Mm-hmm.
Because your t goes to infinity. If your t goes to infinity, the numerator goes into infinity.
Yeah.
What about the denominator? S minus 3 times t. Okay.
That would also go to infinity faster.
Okay. Yeah, you're okay. This is also indeterminate form because you have infinity divided by infinity. Okay, you're fine. My bad.
No, it's okay. So yeah,
Okay.
so using L'Hopital's, it makes it clear that, you know, that the bottom is going to infinity, making this entire thing as it goes to infinity 0. So as such, it would just be solved as 0 plus 0 for 0 to infinity for the left part. For the right part, we can just use the integral, and it will just give us our e to negative s minus 3t from 0 to infinity, and that would just give us, you know, negative 0 plus 1, which will just give us negative 1. And that's it solved, basically.
All right. Nice. Okay. Okay. Anyone has any question? Excuse me. All right. So I'm going to talk about, so we're going to go through these notes. Still Laplace transforms, but with the initial values now. So we'll solve differential equations with constant coefficients using Laplace transforms by transforming the differential equation. So this is similar as before, right? Now by linearity, this A, B, C, those coefficients can go before the Laplace transformation. So to do this, we need the following theorem. Suppose the transformed function is continuous and piecewise differentiable, which means we can ignore finite many points, not differentiable, for t greater than or equal to 0, so t not be negative. And there exists non-negative constants, capital letter M, lowercase c, and capital T, such that the absolute value of the function value is less than is or bounded or less than or equal to such capital M times e raised by ct. For some t greater than this, little t greater than or equal to the capital letter T. Okay, this is very mathematical. If anyone has any question, just let me know. Feel free to stop me. So those are just very mathematical. So basically saying, what's the idea in this? Basically saying, okay, for such, if f is continuous, you forget about some, you know, finite points, not differentiable. And for such t be negative, you know, f of t, the absolute value of t, f of t is bounded by such thing. Some, you know, m is some constant, c is some constant, and the capital T is some constant. For lowercase t greater than or equal to, or means at least capital T. Then the transform of the derivative, first derivative of the function equals to s, well, such s is greater than c, times the transformation of f of t s times, so some number, some scalar with the transformation of f of t minus f of 0. Okay, we can use capital letter F of s to represent the Laplace transformation of lowercase f of t. So we can write it in this way. Some number bigger than c multiplied by the transformation, then minus f of 0. This is the theorem. All right, if you want to go through the proof, let's go through the proof. Yeah, let's go through the proof. So using integration by parts. So let's apply Laplace transformation to this f prime of t, right? By using the definition. So we get this, right? Because when we integrate f prime of t, we just get f of t. S is here. So this is the integration by parts. Then to simplify, after simplifying, what do we get? We get this as S times the transformation of f of t minus f of 0. Or can be written like this, right? So that's the part of this. Okay, that's so the little Q proof, right? Just go through by definition, go through the definition. Now let's see to find the second derivative. Laplace transform the second derivative of f. So assume g of t equals to the first derivative. Yeah. So then g prime of t is f double prime of t. So use the theorem already been proved. That means transform second derivative of f is the same as transform the first derivative of g. And by the theorem, we'll get this. And then what's g of t? G of t is just first derivative. So we have such a beautiful relation. So this is recursive relation. Laplace transform the first derivative, we get s, or better use this, s Laplace transform of f of t minus f of 0. Transform the second derivative, we get s times the Laplace transform the first derivative minus the first derivative evaluated at 0. Right? If we substitute this one into this, right? So what do we get? We get s squared Laplace transform f of t, s squared Laplace transform f of t minus s times f of 0 minus f prime of 0. Beautiful relation, huh? So similarly, we can keep going. We can keep going. Maybe we can write to the nth. Laplace transfer the nth derivative of f has such formula. S raised by n, f of s, Laplace transformation of f of t, minus s raised by n minus 1, f of 0, s raised by n minus 2, f prime of 0, so on and so forth. S times f raised by n minus 2 of 0 minus in the end f raised by n, f to the derivative of n minus 1 of 0. Let's see some examples. So we're given initial conditions x of 0 equals to 7, x prime of 0 equals to 2. And we want to solve this equation, differential equation with those initial values, which means we want to get to a specific solution, right? So we have double prime here, well, first prime here. So let's just transform everything by linearity. So we can write transform of the second derivative, transform the first derivative, transform the function itself. For the second derivative, we can write as s squared with capital letter X. Think about this X as F something. Then S, so what is X? X of S. It's the Laplace of X of T. X S squared Laplace X of T minus S times, used to be F of 0, now X of 0, then minus X prime of 0. And the Laplace of the first derivative, just S with the Laplace X of T minus X of 0. So substituting into the transformed equation, we have X double prime minus X prime minus 2X equals 0. So this is our new X double prime. This is our X prime. This is our 2X. Simplify, because X of 0 is 7. X of 0 is 7. X prime of 0 is 2. So plug in, get our second transformation of the second derivative is this. Transformation of the first derivative is this. So this is transform the function. We have X of S, X of S, X of S. That's the Laplace transformation. So we factor out. Then we have S squared minus S minus 2. So this. Then what's left? Or minus 2, or this minus 7x minus 2 minus negative 7 become plus 7. So negative 2 plus 7, that's plus 2, plus 5. So we have this such equation. To solve for, before use capital letter F of X or Laplace of X of T. So we get 7s minus 5 divided by this, right? 7s minus 5 divided by this, and this can be factored as s minus 2 times s plus 1. Use the partial fractions. Christian already showed us how to do this. Right. So this is a way to do partial fractions, because if we have two factors, we want to write as separately, each factor separately. Then we think, okay, we need a common denominator, right? So that means a multiplied by s plus 1, because this missing s plus 1 to get this form. And this term missing s minus 2, so multiply by s minus 2 divided by itself, get this term. Then simplify, rewrite it. We have ax plus bx, that's a plus bx. Then we have a minus 2b. So we compare with what we have, where we started with, 7s minus 5. The s term, the coefficient has to be 7, so that means a plus b is 7. The constant term, a minus 2b equals negative 5. So we have this system of two equations with two variables, right? Can solve. Then a equals 3, b equals 4. That means we can rewrite this rational expression as two rational expressions. So the little x of t is the inverse Laplace transform of the capital letter x of s, right? So x of t equals the inverse Laplace transform of x of s, which is this we just solved. And we write it in nice form because we want to match up with the Laplace transformations. So that means the inverse Laplace of this, by linearity, we can separate it into 2, and then we can factor out this 3 and this 4. So the inverse of Laplace transform of 1 over s minus 2, that is e to the 2t. Inverse Laplace transform of 1 over s plus 1, that's e to the negative t. So the solution is 3 times e to the 2t plus 4 times e to the negative t. Anyone has any questions? So given a initial value, right, because this is a double the differential equation, the highest derivative is the second derivative. So we need 2 initial conditions, one for the original function, x of 0, and one for first derivative, x prime of 0. And with that given initial conditions, we can solve for a specific solution. Let's see example 2. So this equation is x double prime plus x equals cosine 3t. And the initial condition is x of 0 equals 1, x prime of 0 equals to 0. Okay, we'll apply Laplace transformation. By linearity, we can separate them. Then by the theorem, so Laplace transform s double prime is this. S squared Laplace transform of s of t minus s of x of 0, then minus x prime of 0. Right? Laplace transform of x, just Laplace transform of s. Laplace transform of cosine 3t into s over s squared plus 9. Remember cosine kt, the denominator is x squared plus k squared. So we have s squared, x of s, minus s, because x of 0 just 1. The x prime of 0 is 0. Then we factor out x of s. We factor out those two. Then we have s squared plus 1. Right? Plus 1. Then we have minus s. Right? Minus s, we move to the other side, become plus s. And simplify those two terms, combine those two terms, we get s times s squared plus 9 over s squared plus 9. So then plus s, that becomes s cubed plus 10s in the numerator. Yes, David.
Wait, so the way that you do it for x prime of 0 is you take the value of x at 0 and take the derivative? Is that the order that you do it in?
Which one?
For x prime of 0, you said it equals 0. Do you just take the derivative of whatever x of 0 is?
No, it's given.
Oh, sorry. Okay. Yeah.
This is the initial value problem. It's given.
Okay, I apologize. Sorry.
It's okay. It's good. Good question. Yeah. Yeah. Okay, so we want to solve for x of s, basically Laplace of x of t. And then we combine those two terms. So we get s cubed plus 10s divided by s squared plus 9. Now we want to divide by s squared plus 1 on both sides. So we get x of s, which is the Laplace of x of t, equals to x cubed plus 10s divided by x squared plus 9 times x squared plus 1. Again, we want to use partial fractions. Yeah, because the denominator has squared, s raised by squared, s raised by squared. So the two factors involve the square. So then the numerator, before the denominator was linear. If the denominator was linear, the numerator is just constant. But now the denominator is squared, so the numerator is linear. So on and so forth. If the denominator is a cube, s raised by 3, then the numerator, you have to involve quadratic form. Okay, then use the trick again. We see as plus b needs to multiply s squared plus 1 because we need a common denominator. Then cs plus d need to multiply by x squared plus 9. Then perform the operation of addition. Then compare with the other side. Compare the coefficient of x cubed, which is 1. The coefficient of s, which is 10. The constant term is 0. So we do this. Multiply those two, then combine. Then find the coefficient of x cubed, which is a plus c. Coefficient of s squared, which is b plus d. Coefficient of s is a plus 9c. Then the constant term. So the square term is 0 because we only have 1x cubed plus 10s. So the square term is 0 and the constant term is 0. So that means b plus d is 0 and b plus 9d is 0. A plus c equals to 1. And a plus 9c equals to 10. Okay, so with a, b, c, d, 4 variables, we need 4 equations. Indeed, we get 4 equations, 4 variables, so we can solve. Then from this, b plus d equals 0. Then b plus 9d also equals 0, right? In this case, b equals to negative d. So change this to be negative d. Negative d plus 9d, that's ad. ad equals 0. A is not 0, so that means d has to be 0. If d is 0, that means b has to be 0. So we solve for those two variables, b and d. Where does b and d appear? So b is here, d is here. That means the numerator will only have a number multiplied by s, a number multiplied by s. Let's solve a and c. A and c will have a plus c equals 1, a plus 9c equals 10. We have the system of two equations with the two variables. So we can solve. This thing a equals to negative c, right? Oh no, a equals to 1 minus c, 1 minus c. So we can substitute into here. A equals to 1 minus c, so that's 1 plus ac, right? So ac, move 1 to the other side, so ac equals to 9. So that means c equals 9 over 8. Right, if c equals to 9 over 8, that's 1 and 1/8. Plus a to be negative 1, so a has to be negative 1/8. Okay, with ac solved, we'll put it back in the form. So as is negative 1 over as. Then c is 9 over 8, so still have cs, 9 over as. Now we're in the right form. We have s over s squared plus 3 squared. We have s over s squared plus 1 squared. Remember the 3 squared, 1 squared is a k squared. Okay? So we want to apply inverse of Laplace transform. So little s of t equals to inverse of Laplace of transform. Because this is Laplace of transformation, So this is x of s is L Laplace transform of x of t. Inverse, this is inverse. So L inverse, then L of x of t, that's inverse and inverse and the function, because they undo each other. So x of t. What if C and D? Okay, Jun is asking, what if C and D have a number but AC do not? That's fine. That's fine. Oh, then the fractions still have S in the numerator. Let's see. Okay, that's a good question. You're thinking something. Okay. Jun is saying, let's see here, right? Because we don't have B, we only have AS. Because, you know, we want to get into the form S divided by S squared plus K squared. She's asking, what if this is 0, A is 0? We only have a constant over S squared plus 9 squared. 9 squared. So what can we do? Remember we have K over S squared plus K squared. We can do that. Do you see that? And this constant we can always manufacture, right? Let's see if this is 3, if this is 4, but we need 3 on top. So what do? We just multiply by 3 over 4. We multiply by 1. Right? Whatever we need in the numerator as a constant, we just multiply by its multiplicative inverse. So we can manufacture that. Does that answer your question? Okay, so it still works. It still have inverse transformations. But maybe, because your question extended to maybe sometimes there's no, but for this purpose, you know, for the purpose of this course, the inverse transformations, you know, are doable, okay? Because we have learned this couple of transformations, and we want to apply that. But if it's possible, there's no inverse of transformation to be found, of course, right? Okay. So now we're into the Laplace inverse of transformation. Where am I? Okay, here. S over S squared plus K squared. In this case, it's 3 squared. Right? We know that's cosine KT, cosine 3t. And Laplace inverse transformation S over S squared plus 1. K is 1. That's just cosine 1t. Of course, with these scalars. Okay, anyone has any question? Okay, Laplace transforms can also be used to solve simultaneous differential equations. So that is a system of differential equations with more than one unknown functions, simultaneous differential equations. Oh, the notes ended. The notes ended. So maybe next time we talk about the simultaneous differential equations. Anyone has any questions? I think I was so good with Laplace transforms and the inverse of Laplace transforms. So which is great. Because Laplace transformation is just amazing. Anyone has any questions? If no questions, okay, I have a question to ask. The final exam date and time is scheduled. Let me type in the chat. It's December 14th, of course, 2023 at 8:30 p.m. Scheduled for 2 hours, 10:30 p.m. So this time is scary for me. I'm not a night person at all. You know, when the day gets dark, I just stay home. So I wrote an email to the department chair, Professor Suzuki, ask him if it's possible to change the final exam during the daytime. But then I thought, you know, it may not work for you guys. Maybe you have to go to your jobs during the day. Maybe you have to take the final exam at night. So I want to ask you, do you like this time? The date, December 14th. Let me see, what day is that? December 14th. It's a Thursday. December 14th is a Thursday. Okay, what's come to worse? David, you can do it online. The school requires the final exam to be in person. Oh, yeah. So, you know, before the final exam, so probably I'm going to do this. Before the final exam, I'm going to give a, I don't know if I should do this because the COVID is ending. Because during COVID time, I would give students, if it's an online course, according to their presentations, according to what I know about them, I give them like approximate a grade. If they agree with me, fine, that's gonna be their grades. If they don't agree with me, they think they can do better, you know, then they go to campus, take the final. I'm not sure if I should do this. I have to ask the department chair to if I could do this because the normal COVID. Yes, David.
Wait, so you're saying that you'd give like an approximate grade based on performance before of like what you know about the student, and then they wouldn't take the final?
Yes, that's during the COVID time.
Ah, okay. Yeah, because like you said, like a lot of people have like work and stuff, and so.
Yes. So so I don't know how would this work out. So the worst case is I have to go to a campus. Maybe I have to invite one of my friends to come with me. I'm horrible at the night. I'm just scared of the dark. Anyway, can we do one-day review? Of course, Ronald. Ronald, I need you to present. 30% of the grades come from your presentation. I think we have a lot of time for you to present, all right? So prepare to present. Because if you take the final, if you take the final is going to be more difficult than presentation, I'm telling you, right? For sure it's going to be more difficult than to do presentations. So 30% grades coming from presentation is like a gift, isn't it? Anyway, okay, any other questions? Let me see how, maybe evening time, let me see how, he hasn't replied me yet, because rescheduling has to go through a lot of stuff, has to go through the whole campus thing, have to find an empty room, available time, stuff like that. So let's see how he, replied to me. Then I'll talk to you again. But the final is scheduled. The final is scheduled. It's online. It's December 14, 8:30 to 10:30. Oh, Zoom. The Zoom I don't remember. Is in Ingersoll 6104 something. So once it's finalized, no change, I'm going to post on Blackboard. Yes, David.
Oh, sorry, I just left my hand up.
No. Oh, okay. That's all right. Okay, anyone has any questions? Yes, Suxian.
So you mean, and then we don't need to go to the campus for the final?
I think we have to go on campus for the final.
But I took the class from the Suzuki last semester for the history of math. But he always and then like online because that's online class, and then he have final online too.
Oh, I have to ask him. Okay, if he agrees, I have no problem to do online. I need to ask him.
Because that class, that courses, and then there's supposed another professor. But before the classes start, the professor used to for these courses pass away, so he took over this. So that's why that's
Oh, yeah. Sometimes for special occasions, maybe I don't know.
Well, he's very nice, but he always agree whatever we say. So that's why I talk to him.
Yes, yes.
I'm like during the daytime I can because I have another 2 exams in the campus.
On 14th, right?
Right.
Yes, on 14th.
I have like 2 courses and during the daytime, so that's why like a 14 I have like a 2 final exam, and plus you have 3 final exam.
I see. Hopefully he can change. Let's see how he reply back to me. I have
8:30 too late, and then we will finish like at 10:30. So how can I get home?
Yeah, that's why that's why I wrote to him.
I need to call the Uber. So that's the difficult. Yeah.
That's worst case. Yeah, on 14th I have other 2 exams also, but during the day from 6:45 in the morning until 1:30 in the afternoon. That's fine with me. Let me see how let's just wait a little bit. Let's see how he replies. All right, any other questions? All right, if no questions, you're a free bird, you can start your homework. I'm prepared to present next class. Thank you. Have a good night. Take care. If you want to talk to me, I'm always here. Just worry about it. Yeah.
Have a good night, Professor.
Have a good night, David. Yes, Ronald, you want to talk to me?
Yeah, I'm sorry I couldn't present. It's been so bad for me, so difficult for me to present. I don't know how it's gonna happen. I missed many presentations.
Yeah, you just need to try to. If you want to get 30% of your grades, you just have to try to present every class. Why? You.
I mean, can I present like twice, like two sets of the homework?
Yes, it's possible. It's possible, but it has to be 2 different questions, 2 different types of questions.
No problem. So
okay.
I noticed I'm almost done with the homework, so I could pick any the rest or anything in the middle.
What do you mean the middle?
Like I'm at least we're almost done with the homework. We only left almost done with everything. So I guess we are at homework 6 right now. Last time I checked, we did.
Oh, okay.
We did Laplace transform.
Right.
So we could I could
just choose different questions from just choose different questions, different type of questions from different sections.
Okay.
Okay. All right.
All right. Thank you very much.
You're welcome. Same for Silo. Silo, you never present either.
I don't think he's there. Thank you. Good night, Professor.
You too. Thank you. Keep trying. Liz and Ryan, you don't present anymore. Why? Keep presenting.
Professor, mind if I ask you something?
Yes, go ahead. I missed your presentation.
I know. I'm sorry. It's what I'm about to ask is sort of about that. It's just
Yeah.
I'm taking 23 credits this semester, so I'm swamped with work, so I don't really have a chance
Oh
to
my
do the
goodness.
presentations.
Why you
So
want to do that?
well, it's fun.
Oh, okay.
It's fun,
Study
but
hard. Study
yeah,
hard.
yeah. I mean, I have a lot of classes, but what I was going to ask you is last week, I believe you mentioned you were going to push back the homework by a week because it's a lot of
Yeah.
calculations.
Yes.
I haven't had a chance to do a lot of it, and so I noticed on Blackboard it's due tomorrow, but a week would be Monday. So would you mind if I maybe submit that by the end of the weekend?
Yeah, don't worry about it. Okay.
Okay.
Don't worry about it. But submit anytime you can. What
Yeah.
are other classes you're taking?
I'm taking calc-based physics 2, mechanics, then Java 2, computer ethics, and then along with differential equations, I'm also taking linear algebra.
What's computer ethics?
Ethics. It's
Ethics.
basically don't write malware, don't steal money with your computer, things like that. It's the writing intensive.
Like a moral. Okay, I
yeah.
didn't know such course exists. Okay, that sounds
That's the writing intensive for the computer science major.
We live in a different era totally.
Yeah. Well,
Okay.
thank you, Professor. Again, I'm sorry about the presentations. When we got to series, I did try. I think it was day 13. I sat down and I tried to do it out, but it was right after linear algebra, and I got stuck in linear algebra. And so when I came home, I didn't have much time to look through it, and so
That's okay.
and so I'm kind of still. I'm still a little bit behind on series. I have to pick up on all of that, and then hopefully I might be able to do a few presentations still.
Okay, that sounds good.
Thank you very much. Have
You're
a good
welcome.
night and a
Have
good weekend.
night. You too. Angie, Liz, you girls have questions?
Yes, I have.
Yes, Liz.
My last homework, I submitted it like after the deadline, like I told you, but I see like it's not graded yet, so I don't know if like you receive it or.
When did you say which homework? I have graded everything.
I think it was homework 4.
Homework 4? No, it's not here anymore. I have graded everything. Let me check yours.
Yes, please.
Full grade sent Liz homework 4. I have graded.
Oh, okay, thank you. But it's not showing. I don't know.
Oh, on your side doesn't show. On my
Yeah.
side it shows.
Okay, thank you. Also,
Yeah.
I wanted to present, but just like Ryan, I'm thinking like a lot of classes, and I don't really have time, and I've like kind of fall behind. When I get to the series, I kind of like get a little bit confused because my
we're
previous classes,
gonna review. Okay. So
yeah,
we're going to review. We're going to review. We're gonna go back, review. Let me know where you have questions. That's what I was worried about. Because I
yes.
don't see you guys presenting. I was like, maybe this is too much.
My last presentation, I did it on 13. But moving onto 14, I kind of like feel like lost, so I was just trying to catch up until I can, so I can like present next
All
time.
right, no
I will try.
problem. So okay, you try, and I'm gonna go back to review.
Yes.
Okay.
Yes. I don't know if you have time, so we can look into like 14 like tonight, because I have like some question I wanted to ask.
14, question 14. So hold on one second. So let me ask Anqi. Anqi, do you have any questions? Anqi? Okay, I guess she's not listening. Okay, let me make you presenter so you can share with me. Yes. You're a presenter, you can share your screen with me.
I don't have the picture upload yet, but it's from homework 14 or the slide 14.
From homework, hold on 1 second, from homework 14. Homework 14. Yes, okay. Do you see the screen?
Yes.
Maybe not.
Yes, I can see this.
No, but you don't see. I need to change it. You need to see the questions itself. I want to change to.
Or maybe I can try to take a picture now and then show you.
Do you see it? No, the questions are here, right?
Yes.
Yeah, put on the screen. So which question?
Yes, I started like the first one and then I got like blocked. When I see that we do I try to find like the form of the solution, right? Y prime, Y double prime in terms of like power series. I replace, then I do the reindex. Then I found
Recursive relationship.
yes, the recursive relationship. So far I'm good. But when it's like when we do like for like even numbers like 2, 4, 6, and after we do something like for 1, 3, 5, like I like sort in the notes, but when it's come like to give like the final answer, I don't know like how do I make like the final answer, because
okay. For some questions it might be very difficult to find the pattern.
Yes.
Yeah, I think that's right. That's what you're struggling with. It's difficult to find the pattern. Don't worry too much about that. Don't worry too much about that. As long as you can do this, as long as you can do what you said, you reindex, take the derivative of power series, put it back into the equation, you know, reindex, then find the recursive relation. That's good enough. Sometimes find a specific representative is very difficult. Yeah. Don't worry about that.
Can I share with you?
Sure. You have it ready?
Yes,
yeah,
I
you
just
are a presenter. You can share with me.
okay. It's loading. So
okay.
Can you see it?
Not yet. Oh, let me